So this is just a quick overview of the three parts from this packet. Rate from data, haha, very clever. But the idea, as we build on mechanisms, as we build on experiments, as we build on collision theory, the only way to truly know what speeds up and slows down a reaction is by doing an experiment and measuring that impact. So this packet is grouped into kind of three sections that shows how we can do that. The first here I would call the relative rates or graphing the rates. So here we have several graphs in which we are looking at amounts versus time. Most of the time we're going to be looking at concentration, but sometimes it'll be mass, moles, or other things. So initially we are just looking at how much do I have now. And from math class, maybe from a physics class, you probably know exactly how to find the average, but it's the change in y over the change in t. And we're just calculating those values. But what we're going to start to do is see how the change in one factor impacts the change in the other. That's why we go from the graph of 1 to the graph of 2 here. And as we do that, we can notice it's the same graph. We're just a little bit more spread out to show a higher value. So this graph, looks a little bit cramped up, but we are comparing those things. So as you look at the answers there, I'm just finding a couple values and looking at those changes. But based upon those changes, we can start to not just look at them as numbers, but we can make comparisons. How one chemical changes relative to another. Is it being produced faster or slower? And if it is changing faster or slower, twice as fast, half as fast, 3 times as fast, etc. So on 2 and 3, we're taking specific data that allows us then to make conclusions about the stoichiometry of the reaction. Question 5 is then going to have us apply that. If we see what the pattern is, we can see how one chemical, in this case nitrogen, impacts the rate or how many moles per liter, molarity per second, is being consumed or produced for our other guys. When we have it as, numbers here, we're looking at ratios, we're looking at coefficients, we're looking at a balanced equation. And when we're doing it onto a graph, you don't need every little dot along the way to be perfect. But what we do want to do is to see, well, how much has each chemical changed? So here we're focusing on hydrogen from beginning to end had a change of a certain number of moles. Well, how much should nitrogen change during that time, and how much should ammonia change? I do want you to note that it tells you the initial amount of nitrogen, and it tells you we're going to start our ammonia down at 0. So we can know at what value they should flatten off. We should know at what time, based upon where ammonia flattens off, where hydrogen and nitrogen where ammonia and nitrogen can also flatten off. We don't then need to find every single change or bullet point along the way. We're just understanding that we have a certain curve with a certain steepness here, and then we'll have different curves with steepnesses relative to our rates, or hopefully at this point we're understanding relative to the coefficients. But as we are doing that, we need to know, how can I find the molarity here. It's not just going to jump out and shout at us. It's not necessarily like, oh, it bubbles a little or a lot. We want to quantify it. So right here, this just comes down to some definitions. Some you know, some you don't know. But what is a tool or a factor that can measure something? If you didn't know it, check the answer key and know that that is then a definition. Number 8's a little bit of an extension, a little bit tricky, where we are recognizing how certain things we can measure are super productive, but for other things, it's a little bit harder to know. So just a quick overview there on that front page.